Hello, hello. All right, here we go. Unit 3, Day 7 notes. So our question today is how do we create an open top box? So we've got one type of question that we're trying to look at. We're going to try to figure out how to get our answer. So you can label at the top of this page also that it is a box problem we're working on. So we want to have something that looks like this. We want an open top box that's a rectangular prism. And we want to create that. But we're going to create that from a flat piece of paper or cardboard or some material that's just flat. And we want to figure out how do we create this. So if you have a piece of paper in front of you somewhere, I just want you to think for a moment about how you would create an open top box like this one in the picture. So using that piece of paper, what would you do to actually create this? Would you fold anything? Would you cut anything? So take a moment, just think through that. Okay, so you've thought a little bit about what you would do. Now, what I would do is I'd fold up all the sides, but when I fold up the sides, like if I fold this side up and I fold this side up, I want them to be the same height. So what I'm going to do then is that in this corner, I would want to get rid of that piece. Or in origami, we'd probably use it, and we'd probably use it to like fold and tape together. But if we're looking at a piece of steel to make this, or a piece of wood, we wouldn't really be able to fold it. So we would probably just cut it out. So we're going to cut this, and I would cut at the corner here. So I would cut equal lengths there. However, did I draw equal lengths? No, not necessarily. So how would I tell someone I want to cut equal lengths on both sides? Well, do we know how much we're going to cut on each side? Not necessarily. So I would probably just call it X. And then the other side, I don't know how much I would necessarily cut, so I call that X also. Okay? But that's only one corner. So what I would have to do is actually do this on every corner. And I want to cut the same amount for each corner. Okay, so then, in general, I've got my width here, and I've got my length down here. But something I could figure out about the open top box then, instead of just having an area, I could actually find a volume. So a reminder to us that volume equals length times width times height. And for this example, or in general, if we're looking for volume, our length would end up being the length, but taking away 2 x's. So what do I mean there? Well, here is the length, this whole thing. But when I cut out those sides, so when I actually make this cut here, and make this cut here, then I am decreasing the length of the open top box, the picture like this. I'm decreasing it by 2 x's because I had to cut out x on one side and I had to cut out x on the other side. So that's why my length became length minus 2x. My width then became my width minus 2x also, because I have to cut off this x and cut off this x, right? And then my height, well, whenever I fold those sides up, so when I fold this part up, well, my height will end up being x. So I'll just leave that as x. So this is the generic equation that we'll use as we keep going. So this will be pretty important as we keep going. All right, so let's actually try it with a question so we can kind of wrap our heads around this more. So here is our example. And I'm going to give you some time, or you should have this written in your notes. So example. You are making a rectangular box out of a 16-inch by 20-inch piece of cardboard. The box will be formed by making the cuts shown in the diagram, folding up the sides. You want the box to have the greatest volume possible. And then we're going to ask a couple questions with it. How long should you make the cuts? What is the maximum volume? You want it to have the greatest volume, so what is the maximum volume? And then what are the dimensions of the box, of the finished box? What will they be? Apparently I can't talk, but that's okay. So this is what it'll look like. We already saw something very similar to this. We have 20 inches along the length, we have 16 along the width, and we're going to cut out 2x. And you can kind of see here what those cuts would look like more so. And then our box would look something like this. So we need to figure out what would be how would we actually figure out these answers? How would we figure out how long the cut should be? How would we get the maximum volume? Well, let's start with that. We know volume is length times width times height. So after you've written these questions, maybe draw at least this diagram over on the left side here to help figure out what we're doing. And then write with me your formula for volume. So volume equals length times width times height. And in this case, volume, the length, it was 20 inches, but now we're going to take away x's. So we have 20 minus 2x. And our width was 16, but we take away, so it's 16 minus 2x. And our height ends up then being our x. So in our picture here, our length, this would have been our 20 minus 2x, because we cut those sides. Our width here was 16 minus 2x, and our height here is just our x. So we are multiplying those together to get the volume. Now at this point we could FOIL this all out, but our calculator can do that for us. So let's just go to our calculator and plug this in. So go to your calculator, press y equals, in parentheses we're going to plug these in. So 20 minus 2x, parentheses, next one, 16 minus 2x, and then times x. So I'm going to press zoom 6 just to get me back to where I started, or just back to that standard window. And I see something kind of happening with the graph over here. And it looks like it goes higher than this. So I'm going to change my window. Now, I'm going to keep my x's the same. I think that it looked just fine there. But my y's, I think I want to go a little higher on this one. Because I'm trying to look for my maximum volume. So maybe I'll go to like 100. Now when I change my y max to 100, I want to change my scale to about 10. So I won't have all those lines in between. So let's graph it and see what it looks like. Okay, so I can see a little bit more of it. It seems that I need to go a little bit higher, a little bit lower, maybe a little bit more to the right. So let's change that. A little bit more to the right would be my x maximum. Let's do 20. I'm going to just change the scale to 5 then. My minimum, maybe I'll do negative 50. My maximum, let's try like 400. So I'm going to change my scale to like 50. Okay, let's graph that. Okay, so I see a little bit more, and I see that it's going up here. I don't really know what's happening over there, so I'm going to change that a little bit more. I'll go a little higher and a little lower. So my minimum, maybe I'll do 90, negative 90. My maximum, let's do like 600. Cool, so that looks a little more like what I would imagine, because I had volume is, when we talk about volume, we talk about units cubed, so it should look like a cubic function. So we know that this side is going to continue going down from the graph. All right, so if we look at this, we have zeros, we have a local max, we have a local min, we've got our absolute min is negative infinity, our absolute max is infinity. So what are we trying to figure out? Let's go back to the question. It says, what is the maximum volume? Okay, so we have V here, and we have X here. It says, how long should you make the cuts, and what are the dimensions? Okay, we got a couple questions here. So this has V in it, but in our calculator, we just plug that in for Y. Okay, so that's telling me that X stands for something and Y stands for volume. So I'm going to write that out. I know that my X stands for something. Let's try to figure out what that is. So the X in the question was the height. So that the height is also how much I cut into each side. So we could say that that's the length of the cut. So the X, remember we're X comma Y, which is the length of cut, comma, and then my Y is my volume. Because instead of having V equals in my calculator, I have Y equals. So we want to maximize the volume. So perhaps we want to find an ordered pair. Okay, so let's think on our graph what ordered pair we want. Now, if I look here, okay, if I look at my graph, then I'm trying to maximize the volume. Okay, well, so we're looking for the biggest Y value. So the biggest Y value, well, isn't that infinity? Well, if I had infinity, what would that make the cut? So I'm going to just trace this a little bit, and I'm going to see what that would look like. So if I keep going, see where my cursor is. So if I am making my way towards infinity, the cut that I would make would be 12.34. Okay, well, 12.34. So if I had this side that's 16, and I had to cut 12.34 on one side and 12.34 on another side, wouldn't that, like, basically overlap each other? Yeah, so that doesn't really work. I couldn't have a cut, really, that's bigger than 8, because, or even equal to 8, because if I had a cut of 8 on this side and 8 on this side, well, then it would just run into each other and that whole side would just fall off. So then let's look at our graph. So it should be less than 8, and then we want to maximize our volume. So it looks like we're looking for our local maximum here. So let's do second, calculate, local max, so let's do 4. And we want to go to the left of that, so press enter. And then we want to go to the right, press enter again, and we find our local maximum is right here. So we have this ordered pair that tells us how long we should make the cuts. And on this one it says we should make the cuts 2.945, and our units are inches. So that's our first answer. What is the maximum volume? Well, it looks like it's 420.110 inches cubed. That's our maximum volume. And we got that just from looking at this ordered pair of the local max. So how do we find this? We want to find the local maximum. Good. And then my dimensions. So right now, in X I have this value, in Y I have this value. If I press second, quit, and if I press X again, notice I've got all sorts of math here. Here, let me close that. If I press X again, then I get that same X that we had before. So I'm going to use that. I'm going to say, okay, well, what's 20 minus 2x? Because that's what this part's asking for, the length. 20 minus 2x, plugged it in for me. And then 16 minus 2x, plug that same x in for me so I can get my dimensions just by using my calculator. So that tells me my dimensions are, let's do my length first. So that would be the 20 minus 2x would be 14.110 inches. And we put the time symbol, but we really mean by, because it's a dimension, by 10.110 inches by 2.945 inches. So that would be what my dimensions would be for the finished box. All right, so we've just gone through one example. Let's go through So another example would be very similar. We would change what our 20, we would change to 16 based on whatever the side lengths are, and we'd still look for our local maximum. So in class tomorrow, we're going to practice this more with a bunch of questions. So this one you should have fully written out. You should have your answers with what question they go to. Make sure that you have the correct units on here and units down here. And then I will see you tomorrow in class.